Welcome to Lab 5 for Physics 1 and the analysis of Red Bull stratos. First, let's introduce the analysis. The purpose of this lab is to model the skydive performed by Felix Baumgartner and analyze whether or not he was able to achieve his goal of being the first human to break the sound barrier using fundamental physics principles. We also want to analyze whether or not drag force is a good model for air resistance in this problem. The main physics principle used in this lab was Newton's second fundamental principle, which states that the net force is equal to the mass of the system times the acceleration. The final result found that Felix was able to successfully break the speed of sound and that the drag force is a decent approximation of the air resistance in this problem. Here is a basic illustration of the system at hand. The system is a space astronaut, which is Felix, and the surroundings of the atmosphere and the air around him. There are two main forces that are acting on Felix: the force of gravity, which runs in the negative y-hat direction, and the force of drag, which runs in the positive y-hat direction and is being used to model the air resistance. This force acts opposite to the motion of Felix. There are two main fundamental physics principles that we will use during this lab. The first one is velocity update formula, which is V initial equals V final plus F net over the mass of the system times the time elapsed. And the position update formula, the final position equals the initial position plus velocity average times the time elapsed. Both of these formulas are derived from Newton's second law of motion. Next, here's the drag force formula, which we're using to model the air resistance of Felix. Momentum, which is equal to the mass of the system times the velocity of the system, and the gravity on Earth, which is modeled as m times g, which is equal to 9.8 meters per second squared. This runs in the negative j-hat direction as seen in the previous slide. Here are the initial conditions for this problem. The weight of the system was estimated using the weight of the suit, which was 70 pounds, plus the average weight of the man in the United States, which was 199.8 pounds. This was converted to kilograms, which is 122.47 kilograms. The initial height that he jumped from was 120,000 feet, which is 36,576 meters. Finally, the proportionality constant for B, which will be used in the drag model, is approximated to be 0.009. The velocity of the man initially is also 0 because he jumps from rest. Here's a position velocity update loop. This while loop will make sure that the system will move during the analysis of the velocity of the model. First, we calculate F net by adding up all the forces that we are assuming are acting on Felix during his dive, which in this case are gravity and air resistance. Next, we update the velocity using the velocity update formula derived from the momentum update formula. Then we update the position of the ball so that the loop continues. The rest of the loop makes sure that we can illustrate the movement of the system using the arrows to represent the forces acting on Felix. Here are the results of the computational model. As you expected, the velocity increases in magnitude after he jumps. He eventually reaches a terminal velocity around 360 meters per second, which is greater than the speed of sound. This model validates that he reached the speed of sound. Possible sources of error. There may have been other forces that were acting on Felix that were not accounted for in the model. Here we only accounted for the gravity and the drag force. The program modeled Felix as a sphere, which could affect the results drastically because air resistance could have had much more of an effect with the increased surface area of Felix's body. Drag could have been an underestimation for the force that models air resistance. What does it mean? What is an appropriate model for air resistance in this problem? This model used drag as a model for air resistance for the problem. It did a pretty good job modeling the velocity and position of the man, as it accurately predicted the time he broke the speed of sound and was roughly close to his actual top speed during the skydive, as we saw in the velocity versus time and position versus time graphs. What if question? What if Felix's suit did not have any insulation? Using the delta E thermal equation, which is equal to the mass times the heat capacity times the change in temperature between the system and the surroundings, we can estimate what would happen if Felix's suit did not have any insulation. Because the difference in temperature between Felix, which is 98 degrees Fahrenheit, and the temperature in space, which is around 57 degrees Fahrenheit, there will be lots of heat transfer from the system, which is Felix, to the surroundings, which is the atmosphere. This results in a negative Q. This would result in making Felix's body very cold and could result in dangerous hypothermia.